Before the first oceanographic dredge ever pulled an animal from the deep Atlantic, scientists genuinely believed nothing could live down there. Not because they were careless, because the pressure, the cold, and the absolute darkness seemed to rule it out. Then, in 1879, a colleague of French zoologist Alphonse Milne Edwards hauled a small net through the Gulf of Mexico, and something came up that changed the argument permanently. It was an isopod, an armoured, segmented crustacean, like the woodlouse you might find under a whetstone in a garden, except this one came from the deep sea, and it was enormous. That discovery forced a reckoning. If a creature this size, this structured, this unmistakably alive could survive down there, then the deep ocean was not a void. It was a world. And the giant isopod was proof. The species that Milne Edwards formally described after that first specimen is known as Bathynomus giganteus. It belongs to a genus, Bathynomus, that contains multiple species, most of them poorly studied even now. Bathynomus giganteus is widely regarded as the largest isopod in the world, though the source material is careful to note that other species within the genus may reach comparable sizes. That qualification matters. It means the known record holder might share that status, and we simply lack the measurements to be certain. The animal is a bottom dweller. It lives on the seafloor of the Atlantic, Pacific, and Indian Oceans, which means its range is not some narrow trench or obscure basin. It spans 3 of the planet's major ocean systems. Its role down there, as best as current evidence defines it, is scavenger. It processes what falls: dead fish, organic debris, whatever sinks from the sunlit water column far above. In an environment where food arrives unpredictably and energy must be conserved, a creature built for patience and opportunism has an advantage. The resemblance to the common woodlouse is not superficial. Giant isopods and terrestrial woodlice are genuinely related. Both belong to the order Isopoda, a group that spans marine, freshwater, and land environments in a way that few crustacean lineages manage. Looking at a giant isopod photograph for the first time, the segmented armour, the paired legs, the rounded body profile, it reads as familiar even though nothing about the deep ocean is familiar. That contradiction is part of why the 1879 discovery hit the scientific community so hard. At the time, the idea of a lifeless deep ocean, the so-called Azoic hypothesis, had only recently been challenged. Sir Charles Wyville Thomson and others had already begun presenting evidence that life existed at depth. But a juvenile male isopod dredged from the Gulf of Mexico, visibly related to a creature anyone could find under garden debris, made the argument concrete in a way that specimens of sediment or microscopic organisms could not. And then, for over a decade, that was all there was. No females were recovered until 1891. The gap itself is a measurement of how difficult this environment is to sample. Here is where the story of deep-sea giants becomes more complicated and more interesting. Bathynomus giganteus does not stand alone. The deep ocean appears to favour scale in certain lineages through a phenomenon biologists call deep-sea gigantism, a pattern in which organisms living at depth grow significantly larger than their shallow water or terrestrial relatives. The mechanisms behind this pattern are still debated, but the pattern itself shows up across unrelated animal groups. One of the clearest examples comes from the amphipods, a different crustacean group, shrimp-like in general appearance, normally small enough to hold between 2 fingers. Alicella gigantea, sometimes called the supergiant amphipod, is an amphipod that reaches up to 34 centimeters in length. That is not a rounding error or a disputed outlier measurement. 34 centimeters places it in a category of size that challenges any casual assumption about what an amphipod is. Like Bathynomus giganteus, Alicella gigantea inhabits the deep sea. And like Bathynomus giganteus, it represents a lineage that, in shallow water and on land, exists at a fraction of that scale. The parallel is not coincidental. These two animals from entirely different crustacean groups arrived at unusual size through the same environmental pressure system, the deep ocean, and they remain among the largest known examples of their respective orders. What neither of them fully resolves is the core question that deep-sea gigantism keeps raising. Why here, and why these lineages? Cold temperature, reduced metabolic rate, and extended lifespan are among the proposed contributors. So is reduced predation pressure at certain depths, which might allow animals to grow beyond the sizes that natural selection would trim back in a more dangerous water column. But these remain interpretations, not confirmed mechanisms. The source material does not establish a tested causal explanation, and any narration that claimed otherwise would be going beyond the evidence. What the evidence does support is this: the giant Isopod's 1879 discovery did not just add a species to a list, it shifted the frame. It demonstrated that the deep ocean could sustain complex, large-bodied, active animals with sensory structures, with behavioral repertoires, with ecological roles. And in doing so, it made every subsequent discovery easier to accept, including Alicella gigantea and whatever else remains to be formally described from the genus Bathynomus, where multiple species are still considered comparably poorly known. That last phrase deserves a moment, comparably poorly known. In a genus that contains what may be the world's largest isopod, described by science in the 19th century, distributed across 3 ocean basins, multiple species remain poorly characterized. Not because the science is inadequate, but because the environment makes sampling genuinely difficult. Getting a net or a camera or a baited trap to the right depth, in the right location, at the right time, and then recovering it with anything intact, each step carries a real probability of failure. The 1891 female, the first female Bathynomus giganteus ever recorded, waited 12 years after the initial juvenile male simply because the opportunity to collect her had not arisen. That gap is not a mystery. It is a measurement of how uneven access to the deep seafloor remains, even now. The giant isopod stands at an interesting intersection. It is large enough to have surprised 19th century zoologists. It is ancient enough in lineage to appear almost architectural, like something assembled from an earlier design. It is common enough across 3 ocean systems to be considered abundant, and yet most of what happens in its life, where it goes between samples, how it behaves in the dark, what the full scope of the genus actually contains, remains outside confirmed observation. The unresolved question is not dramatic, it is precise. Within the genus Bathynomus, how many species exist, and which of them reach sizes comparable to Bathynomus giganteus? The current record may be shared. We do not yet have the specimens and measurements to answer that. What the ocean offers here is not a mystery in the theatrical sense. It is a measurement problem at scale. 3 ocean basins, abyssal plains, a genus of armored scavengers distributed across all of them, with multiple species still poorly described. The instruments exist. The expeditions continue. But the ocean is large, and the seafloor is not cooperative, and the animal doing the waiting down there has been waiting far longer than we have been asking questions about it.